continue to explain thermal interference management for groundwater heat pumps. What you see here on the left side is a thermal plume picture. So if you use groundwater, for example, for heating, then you inject back cold water. This cold water is distributed in the aquifer, so it's transported by the groundwater due to the hydraulic conditions, so due to hydraulic conductivity, aquifer thickness, the hydraulic gradient, and the groundwater flow velocity. So of course, then if you have different systems using the groundwater, and of course you can have a thermal interference of groundwater heat pump systems if they are installed in the groundwater flow direction. So you can have a negative influence here. For example, if you have the groundwater use for cooling upstream, and then you inject back warmer water. This warmer water reaches then a unit downstream in the groundwater flow direction. And of course, if this unit wants to use the groundwater also for cooling, it's get warmer water. And then this is not so favorable for cooling, of course. So the efficiency of the system is decreasing. You can have this influence also if you use that for heating, of course. So if a unit wants to use the groundwater for heating upstream, and then it inject back cooler water. This cooler water reaches another utilization downstream in the groundwater flow direction, and then this system gets cooler water, which means the source temperature for the heat pump will be cooler. So the heat pump needs more electricity to increase the temperature level to that temperature level, what you need for heating up your household. So the efficiency of this system is decreasing as well. This is, of course, what we want to avoid and manage a little bit. But on the other side, also thermal interference of groundwater heat pumps can have a positive effect. So if you have the possibility to install systems which actually use synergies. So if you have a groundwater use for heating upstream and then inject back cooler water, and then you have downstream unit which use the groundwater for cooling, then of course it gets cooler water as a source temperature, and this is quite very favorable for the cooling system. And this can be also happen, of course, for heating. And if you use the groundwater for cooling upstream and use the groundwater for heating downstream, then the downstream system gets a warmer temperature, and that increases the system because the heat pumps need not so much electrical energy. Of course, you can use also groundwater for heating and cooling, and so cooling in summer and heating in wintertime, and this is quite very favorable for the system efficiency. But of course, it's also favorable for the impact on the groundwater, on the aquifer, because it's balancing out a little bit the impact, because there is a mixture of then injected cold and hot water and an overlaying, and the impact on the temperature difference and change downstream is actually a little bit lower down. Also, this must be managed somehow, of course. And then at the end, we have to calculate the thermal interference. So what is the thermal plume and how does the thermal plume behave downstream? If you have small common cases, then you can use simplified methodologies to calculate the thermal plume, so analytical based models. For that, there are some models on the market. So, for example, the groundwater energy designer, or also other analytical models. If you have a larger scales and a complex design of your system with a lot of more wells and so on, and a lot more volume flux, for example, then you have to use numerical software. So you have to simulate in a numerical way the propagation of the thermal plume. For this issue, a lot of other models are available, and software like VFlow, ModFlowSpring, Schema, pFlowtran, which can be used for flow and heat simulations. Here on the left side, you see a simulation. It's made with analytical models for a quartier. So what we try to find out is an optimal locations for the injection and production wells to use the whole potential of such an area. Here, the red dots are the production wells and the crosses are the injection wells. On the left side, you see a simulation in a steady case. So we try to simulate what is the utilization on peak load situation. But of course, you do not have the peak loads at the same time, and you have seasonal use or seasonal variations here, of course. So if you simulate that in a dynamic case, then the thermal plumes are maybe not so large anymore, and you can implement a lot more systems which are not influencing each other in a negative way. So it's quite good to simulate that also in a dynamic case. And of course, if you have to put up a numerical model, then first of all, you have to gather all data for the geological and hydrogeological conditions and build up a hydrogeological model and then transfer that to a numerical model. So you have to design the grid and you have to assign boundary conditions and all these model parameters. Then you calibrate the model with observation data, so ground wall head measurements, for example, or also temperature measurements, and you can do a sensitivity analysis, and then you can conduct the prediction of your thermal plume. You see the same workflow here in another picture. So gathering input data, put up a structure, assign properties and boundary conditions, define the model domain, and then start the simulations, and then compare it again with your measurements. And here you see a picture with a complex situation. So you have several wells using groundwater for cooling or heating. You see that if you use it for cooling, you have a warm plume. If you use it for heating, you get a cold plume. And on the top, you see also a system which uses it for heating and cooling. So it's overlaying the cold and hot plume. And in such a situation, you need a numerical model.